Newton proposed that light is made up of particles. So when you're looking at a bulb, for example, he would imagine, I mean, there were no bulbs back then, but if there was, then he would imagine bullets coming out of these bulbs, and that's what light was, particles. He called them corpuscles. On the other hand, a Dutch physicist named Christian Huygens, and that's not how you pronounce his name. Turns out that his name is pronounced somewhat like Huygens or something like that. But I'm just gonna go ahead and call him Huygens. He proposed that maybe light is not particles, but instead light is made of waves, very similar to the waves in water. And I want to explore, the goal of this video is to explore this wave nature of light. So one question we could be having is, when it comes to water particles or waves in water, the water particles are the ones that are doing the vibrations, right? When you disturb, when you disturb still water, then the disturbance is carried away by the vibrating water molecules. But in light, what particles are vibrating? That's a question that you can immediately ask Huygens, because he's claiming light to be a wave. Well, back then, Huygens and a bunch of other folks assumed that there are particles everywhere in the universe, and this medium, which consists of these particles, they called it the ether medium. This was a very popular notion back then. Ether medium. They assumed that this medium was everywhere, sort of like air. You can't see it, but you can't even feel it, but it's there. That's what they said. Okay, and Huygens says that light is vibration. Light is, light waves are carried by the vibrations of the ether medium. So light is propagated by the vibrations of the ether medium. Now, if you want to visualize something like that, here's our animation. Here's a light bulb, and these particles are the particles of the ether medium that's present everywhere in the universe. And this is how Huygens imagined it. Light is basically disturbance propagated by the vibrations of the ether particle. Ripples. Light is ripples in the ether medium. Beautiful, right? Well, now there's one difference, big difference between the ripples of light and the ripples of water. Water, these waves are on the surface, which is 2 dimensions. And so these ripples are indeed circular, and you may have seen them. But light is a wave in 3 dimensions. So although you can't see this in this diagram, it's in 3 dimensions. So these ripples are not circles, but these are spherical ripples. That's a major difference that you're finding. So this is a 3D wave. But now we can ask a question. We can ask, what exactly are these ripples? Whether you consider light or whether you consider water, what exactly are those ripples? So let me get rid of this and talk about that. So what exactly are these ripples? Well, in physics, these ripples have a very technical and fancy name. We call them wavefronts. And you'll keep hearing this word over and over again in the future videos. So let's clarify what these wavefronts are. Well, wavefronts, let me just define them first and I'll show you. Wavefronts are basically set of particles which are in sync with each other, which are vibrating in sync. And again, there is a technical term for particles vibrating in sync with each other. We call them in phase with each other. We just need to familiarize ourselves with these technical terms. So what do I mean by this? Well, if I come over here and look at one of these ripples or wavefronts and concentrate just on them, what I will find now is that every particle on that ripple or on that wavefront is at the topmost position. And that's why that ripple is a crest. A little later in time, we'll find all those particles will be at the bottommost position, forming a trough. Let me show you one more, which is already a trough over here. We usually denote trough by dotted lines. A trough, if I look at that particular ripple, then you'll find all the particles on that are at their bottommost position. The important thing to note is that all the particles on these circles, they are always vibrating in sync with each other. They're vibrating together in phase with each other. Such a set of particles is what we call a wavefront. And the same would be true for our light as well. Again, let me bring back that visualization. If I were to concentrate on one of those spheres and just look at those spheres, what you are finding now is, look, all the particles on that spheres are vibrating in sync with each other. You see that? Look at it one more time. All right, there you go. Look at that. They are vibrating in sync with each other. Such a set of particles which are vibrating in sync with each other are what we call wavefronts. The last question I want to explore is what in general would be the shape of these wavefronts? Well, think about water first. If you were to disturb it at only one place, at just one tiny spot, then you'll get these nice circular ripples or circular wavefronts. But if you were to disturb this all around with your hand everywhere, then the wavefronts are going to be all messed up and will have weird shapes, right? Same would be the case with light as well. Again, looking at that animation, if the light source that we're dealing with is pretty tiny, or we're looking a little bit far away so that the bulb appears tiny, then the wavefronts are going to be spherical in nature, just like those ripples. But if you were to have a big source, or if you were to go very close to that light bulb where you can no longer neglect the size, the very close to that light bulb, the wavefronts won't be spherical. They might have different shapes depending upon the shape or the size of this light source. But if you go far away, a little bit far away, where it appears to be a point, then the shape is going to become spherical. But I want you now to pause this video and think a little bit about what would be the shape of the wavefront if we were to go really, really far away from this light bulb. Think about that. That sphere is going to become really, really big. What now would be the shape of that wavefront? Can you pause the video and think a little bit about that? All right. If we were to go really far away, that sphere would become so big that the sphere would appear flat to us, just like how Earth appears flat to us when we look at it from a small distance, right? So let me show you that. If you were to go really far away from this, and we'll do that in a second. Now, there we go. If we go really far away, go really, really far away, then look at this. This is a sphere, of course, but what we are seeing now is not a line. Remember, it's in 3 dimensions, is flat surfaces. So now we are getting flat ripples or flat or plane wavefronts. That's what we call them, plane wavefronts. Okay, so usually, what would be the shape of these wavefronts? Well, if you're dealing with, say, point sources, then the shape is going to be spherical. As we saw. In 2D, they are going to be circular. But if you're dealing with point sources or sources which are very far away, you can think of them as infinitely far away. So sources far away, then the wavefronts, the shape is going to be plane. They're going to be flat wavefronts. So the light that we're getting from the sun, for example, on the Earth, the light is so far away from the sun that we can assume that the wavefronts or the ripples of light coming from the sun are plane wavefronts. Now, before I end the video, remember that there is no ether medium. It has been proved in a beautiful experiment that doesn't exist. And light is a much more complicated wave. You may have heard of it as an electromagnetic wave. But when we start learning about light as a wave, we like to start with Huygens theory because it's simple and it can make some really, really good predictions.
Slide, and I would like to start with the question, what is a wavefront, which was asked in 2014 March. So a very important concept. So let me start with a light source. You can take any light source, bulb or candle, like that. So I treat this light source as a point source, like this. Assume that this point source is emitting the light waves in all directions, just like this. So assume that these are the light waves. They are traveling or they are spreading from this point source from all directions. But I have not taken in the backward direction. I have taken only in forward directions. Then from this point source, all these waves, they are traveling certain distance in certain interval of time, and they are reaching the points 1, 2, 3, 4 and 5. Assume that all these points are at equal distance from this point source. Then if you join all these points 1, 2, 3, 4 and 5, by a surface, then this surface will be called as primary wavefront. Primary wavefront because first of all this is a wavefront. Wavefront because this is a surface of a constant phase. All these waves from this point source, they are reaching this surface in equal time, and after reaching this surface all these waves are in phase. That is the reason this surface of a constant phase is called a wavefront. But any reference wavefront will be called as a primary wavefront, not necessarily first one. You can take any wavefront like sixth or hundredth wavefront. If you start with any one particular wavefront, that wavefront will be called as primary wavefront. And after that, whatever the wavefront that you are going to locate or subsequent wavefront from that reference wavefront, the remaining wavefront will be called as secondary wavefront. Assume that this primary wavefront is traveling with a speed v, and in a certain interval of time t seconds, they will cover a distance vt. Distance equal to speed multiplied by time. The speed of this light wave is v, and how much time they are taking, t seconds. So they are going to cover a distance vt. So by taking distance vt as a radius, and these points 1 2 3 4 5, these points on this primary wavefront, if you treat it as a independent light source, you have to treat 1 2 3 4 5, not necessarily 5 points. You can take any number of points. Any point on this primary wavefront will be treated as an independent light source. And by taking these points on the primary wavefront as a center, and by taking the distance traveled in t seconds, that is vt, as a radius, if you draw the sphere around each point like this, this is a wavelet. This first point will be called as wavelet, or in plural form you can call it as wavelets. So I have drawn a sphere around the first wavelet. So like that, and the radius of this sphere will be equals to v into t. So by in a similar way, if you draw the sphere around each point on this primary wavefront, you will have a sphere like this, isn't it? Then you have to draw the one more surface which so that it touches all these spheres like this. So I have drawn the surface. It has touched all the 5 spheres. Then this surface will be called as secondary wavefront. This one is a first one is a primary wavefront, not necessarily first one. You can take any particular wavefront. Then after t seconds, the next wavefront will be called as secondary wavefront. So I think you have understood what is wavefront. So wavefront is nothing but it's a surface of constant phase, the surface on which all the light waves they are reaching, and after reaching that particular surface they will be in phase. Then any reference wavefront will be called as primary wavefront, and subsequent wavefront are called secondary wavefront. Now let me explain about the. So let us start with another concept, spherical wavefront. We have already discussed about the wavefront. So what is wavefront? Basically wavefront is a surface of constant phase. If anybody asks what is wavefront, the very simple answer is surface of constant phase is called wavefront. But since it is a two-dimensional figure, you can't show in a two-dimensional figure three-dimensional effect. But basically if you take a point source and if you take the spreading of light waves in all directions, then the surface that we are going to construct, it is not a two-dimensional one, it's a three-dimensional. That means it will be having a spherical symmetry. It is the surface that you are going to construct around the point source, it will be in a spherical shape. Say for example this is a point source, and this point source, if I construct one three-dimensional surface, then you will have like the surface like this. So point source is at the center, and the spherical surface around the point source is like this. So this is a surface, this is a surface which is having a constant phase which is around the point source, and this constant a surface of a constant phase in the form of sphere will be called as spherical wavefront. So spherical wavefront is nothing but it's a wavefront for the point source which is in the form of sphere. Or you can answer like this, so what is the spherical wavefront? If question is like this, the answer is very simple. For any point source, for any point source, a surface of a constant phase is called spherical wavefront. So what is wavefront? Wavefront is a surface of constant phase. And what is a spherical wavefront? Spherical wavefront is a surface of a constant phase for a point source. For only point source you will be having a spherical wavefront. And this is a cylindrical wavefront. In this cylindrical wavefront I have to take a line source like this. So this is a line source, vertical line, and that vertical line is now emitting the light in all directions just like a tube light. So tube light is a line source. So I have taken a point source in the previous concept, uh, but in this concept I have taken line source. And assume that this line source is emitting the light in all directions like this. This arrow mark indicating the spreading of light in all directions. I have taken only 3 positions, but assume that this spreading is taking place along the whole length of the line source, not just at 3 points. Just for the understanding purpose, I have taken only 3 points. Assume that this spreading is taking place along the whole length of this line source. And assume that after certain interval of time, and these waves emitting from this line source, they are reaching certain points like this. These arrow points indicating these are the points reached by the waves, light waves emitted from the line source. And if you join all these points surrounding that line source, then you will have a surface which is in the form of a cylinder like this. I have constructed a cylindrical surface around the line source, and this surface is having a constant phase because from this line source the waves emitting from this line source reaching this imaginary surface which is in the form of a cylinder. After reaching this surface, all waves are in phase. That is the reason this surface is called as surface of constant phase. It is also called as wavefront. But since this surface of a constant phase is in the form of cylinder, we can call this wavefront as cylindrical wavefront. Hopes you understood the concept. Now let us move to another type of wavefront, a plane wavefront. So for the plane wavefront, I have to start from again point source, and I have to take primary wavefront and secondary wavefront. Assume that this is a point source, and around the point source a spherical wavefront is formed, and that spherical wavefront is now traveling with a speed v. And if you take a part of this spherical wavefront which is very near to this point source, then it will be a curved surface like this. I have taken, because this is a curved portion, means this is a spherical, a part of spherical wavefront which is spreading from this point source, but it is slightly away from this point source, and these two wavefronts are very near to this point source. But I am taking a part of spherical wavefront far away from this point source. So now it is still in the curved portion. So I still go further away from this point source. You can observe here. If I take this part, it will be almost a straight line. If you go further away from this point source, then if you take a part of a spherical wavefront, a part of spherical wavefront, it will be like a plane. It will be like a plane surface like this. It will be like a plane surface. And this is plane surface having a constant phase because the waves emitting from this point source, they are reaching this surface in equal time, and after reaching this surface they will be in phase. The waves spreading from this point source, they are reaching this plane surface. Once they reach the plane surface, they will be in phase, and hence this surface will be called as plane wavefront. So answer is very simple. What is plane wavefront? So plane wavefront is a part of spherical wavefront or part of cylindrical wavefront. Not necessarily it's a part of spherical wavefront. You can take a part of cylindrical wavefront also. So part of spherical wavefront or cylindrical wavefront is called plane wavefront. So now coming to this conclusion part, where we have got three types of wavefront. First one is a spherical wavefront, second one is a cylindrical wavefront, and third one is a plane wavefront. It's like a revision. Let us start with the spherical wavefront. What is spherical wavefront? For a point source, surface of a constant phase is called spherical wavefront. What is the shape of, or what is the shape of this spherical wavefront? It is like this. This is a point source, and these points are called wavelet because these are the points taken on the primary wavefront. These are called wavelets, and the subsequent wavefront will be called as a new wavefront or secondary wavefront. In the examination, this diagram is more than enough. Then if I take a cylindrical wavefront, so cylindrical wavefront, if you take a wavefront for the line source, not for a point source, if you take a surface for the point source, it will be in the form of sphere. But if you take the surface of a constant phase for the line source, then it will be called as cylindrical wavefront. So this diagram is more than enough. You have to show one line source and a surface around the line source which is in the form of cylinder. You have to construct the surface around the line source. Obviously it is in the form of cylinder, and this wavefront will be called as cylindrical wavefront. And if you take a part of either spherical or cylindrical wavefront, will be called as plane wavefront. So this is a plane wavefront. Even for the plane wavefront, we have a primary wavefront and secondary wavefront. So any reference wavefront will be called as a primary plane wavefront. The subsequent wavefront will be called as a secondary plane wavefront.